Hello, this video is mainly just to give you a quick overview of how we might go about using Ecodial for simulating our electrical installation for this assignment. So just to recap on the assignment, you've been provided some details or a load schedule for a particular installation in terms of the density for different services, floor area, and cable routes for 5 different sub-distribution boards fed up a main board. And you were also provided with the solution for one of those circuits. And I'm going to show you briefly how we might input that information into Ecodial and then simulate this solution. So I have Ecodial open here on my own device. If you're going through this on your own device or in the college computers, you would have been asked to log in first. So that procedure will have to be done beforehand. But this file here will be made available to you on Brightspace, and this is just a bit of starter setup file just so you can kind of expedite the process. But I'll open up this project and we'll compare it to what's in the load schedule. So the way this program works is on the left here we have our design, and our view at the moment is single line diagram. So we have a single line diagram for an installation here. We have devices that we can add into our single line diagram. So loads, coupling, UPS, LV transformers, feeder circuits, and the list goes on. And the way I've constructed it so far as a starter for ye is I've provided an LV source. Our main board is represented with this buzz bar here. A cable feeding into our first sub-distribution board, and then a number of loads coming off that. So you'll see when you open this simulation first, the calculation results shown up here will all be 0, and the solution for all of the different parts of the circuit will also not be provided until you run the solution. Now, we have to provide some information, and that comes in the form of the load schedule. So you'll see here we've done out circuit 1. All we have is lighting, general services, and some mechanical services. So that's represented here on this circuit as we have a lighting circuit, general services, and mechanical services, which in this case is a motor. So how we go about putting that information in is, if we have a look, we'll see here we can design it for power or current. So if we go back to I'll split these across the screen. If we go back to our simulation, our lighting circuit here, for example, when we select the lighting circuit, it'll bring up a number of bits of information about the lighting circuit on the right-hand side of the properties bar. In terms in the type of verting, the design current, the cable length, the type of lamp, the output per lamp. So we can provide a number of different design considerations for that. So because I've done out my calculations previously, as in this is going to be the line current for this, I can put that line current straight into this design. In fact, I've done it already. It says 11.766, but I'm putting in 12 just for simplicity. And then we have a cable length. Again, this was left up to yourselves. I'm going to leave it at 15 meters. It doesn't have a huge, sorry, not that it won't make a huge difference, but I haven't specified that, so it's up to you. So these are the basic designs for the lighting circuit, but we can go into smaller aspects of it. So we can actually select the lights themselves, determine the power factor, number of circuits. Again, we've designed it with just the current, so that's enough for us today. The installation method for the cable, I've left this up to you as well, but I've picked 15 meters copper, PVC, multi-core, and we can put in the installation method here. So I've done installation method E. And then the protection device, we can pick this ourselves, or we can let Ecodial do the hard work and pick it for us. And I've repeated that process then for the general services, because that's the next one to consider. We worked out it's going to be 8 amps on on our line current. Well, 7.8, but I'm putting in 8 here just for the sake of it. I'd say it's a 5 meter run. We could also design it using the power values. If we wanted to put in 5 kilowatts or 5.4 kVA, we could do that also. And yes, we can go from there. So, um, actually, I designed that one, I think, with the power in mind instead of the current, but the same idea. It'll auto adjust everything else. Same thing again, we have specifics about the load, the installation method, and the protection device, but I'm leaving those blank. Then our final load on this first circuit is our mechanical services. In this case, it's just a motor circuit. Now, for designing a motor circuit in Ecodial, it asks you to use this motor wizard. So when we launch the motor wizard, what we'll see is we can design a motor based on some predetermined power outputs. So in this case, the motor associated with this load here is coming out at 2.8 kilowatts. So that's based on the design current. So the closest I have to that in my motor wizard is 3 kilowatts. And I think that'll be enough for this solution here. So that's just a quick run through on how you go about designing the different circuits for the first circuit on this whole installation. So again, to break it down, we've got our LV source. This buzz bar represents our main board. We've got a cable feeding our sub-distribution board. And in fact, I've put in the details from our load schedule into that. So we said it's a 20-meter run. So make sure that's set to 20 meters. And that should be enough there. It's three-phase neutral. And that first board now then is ready for simulation. So at this point, we've told it what's in the circuit, and if we use the calculate project option up here, it'll try to size the rest of the remaining components for us. So we go through the process, we'll calculate the network, and we'll see a solution is brought up. And we can zoom in then as to what is being brought up. So it says, okay, here's the protection devices that we think you need for these circuits. So 10 amp breakers on each of those. It also suggests suitable conductor sizes for the phase and protective conductors as well across the board. So it's saying 1.5 is enough for each of those circuits. And it's also sized a conductor for our main cable run and switch sizes and protective devices on that cable too. Another neat feature of this software is that if we go up here to calculation results, it changes the data supplied at each part. And what it actually shows up then is fault currents associated with each of these devices. So three phase, single phase, and earth faults, both drops across cables, and incoming fault levels as well. We scroll down a little bit. Again, fault drops across cables, adjusted design currents based on the insulation methods, fault currents at this board, and that repeats them for each circuit as well. And as we're going into the details of the circuit and the design of the circuit, each of these values, if you're not sure what each of these mean, if you hover your mouse over them, it gives you a breakdown as to what each of them means. So for instance, IB or IR, how we use that. Um, so, explore the software, use it, and try spend some time to get used to it. But what we're trying to get out of this piece of software is, we've done some hand calculations with our load schedule to basically work out, okay, what do we need to put into our simulation. You also, if you've gone through the process, is on the assignment brief. You would also be aware then that there is some hand calculations beforehand, and we're looking for a comparison then between the two. So tonight really is just about, at minimum, getting through the simulation aspect, and the results coming from Ecodial mean you can compare them to the rest of the hand calculations throughout here. Okay. So things that you want to be taken away from tonight are a list of the fault currents, because you can compare them to your hand calculations. But what's also going to be important for those hand calculations, if we go back to the brief, is if we're using our adiabatic equation, we'll need to know the values associated with fault currents, which are easily calculated. The K value, which corresponds to our conductor, that can be got from the regulations, and the time aspect of our faults. So one of the things we can go into here is that when a protective device has been sized for our installation, we can go into the actual details of the breaker and find out the tripping characteristics of it as well. We can also turn it on and off if we need, but we can get the tripping characteristics of this particular device as well. So, and all the information from this can be exported. You can see on the page at the right there, we can export these tables for all the listed devices used in our solutions. Now, the list corresponding to the breakers. Yes, here we go. So I'm going to close off that, look at a particular circuit, and sorry. So this particular breaker, we'll see here the option for curves for the breakers is also offered up. So you can see here that each of the breakers is labeled, for example, QA13, and we can, if you wanted, you could set particular tripping characteristics with that. But we can use these curves then to work out the tripping times for the different faults. So for example, in a worst case scenario, it's saying if we're going to have 902 amps in this single phase fault at subboard 1, we can use that current value to work out a tripping time for this breaker. So coming up 900 amps, it looks like it's going to be instantaneous. And in that case, then we can work out a time, and that corresponds back to our adiabatic equation here. So again, this has been provided as a piece of starter code. At this point, then, you want to be starting to build on that circuit as well. So this is all circuit 1. To add in more elements, it's just a case of adding them in using the edit tool here. So for circuit 2, for example, we'll provide it with a protection, wiring, and switch. Let's put it here, for example. We would then provide a bus bar, sorry. We can extend that out if needed. And then each of the loads off that can be added. So if we go back to our load schedule and go to circuit 2, it looks like we're going to have lighting, small power for desk lighting, general services, and mechanical services. So each of those are a load we can use here. We can have a lighting load, a general load, general services, so sockets, and mechanical service of that. And then in the same approach, you will add in each of the individual components from your load schedule, length of this cable, repeat the calculations, and see what the results look like. Okay.